In this video, I'd like to talk about TokenHMR that proposes a new method for 3D human mesh reconstruction from an image. You can see some of the samples here that it can accurately estimate the human mesh in challenging poses, that there is significant difference between this TokenHMR and HMR2 from ICCV 2023. So let's talk about what are the limitations currently and how this TokenHMR can solve it. But before talking about this paper, let's just talk about how we can represent 3D human mesh. It is by a method called SMPL or simple that we can reconstruct any sort of 3D human mesh by two sort of parameters. One is theta parameter or pose, that is a 72-dimensional vector. Why 72? Because we have 24 joints like shoulders and elbows and wrists and ankles and so on, and each of them are represented in a 3 dimension. But note that this 3 doesn't mean an actual 3D coordinate. It is an Euler angle representation, and it means how much we should rotate in X and Y and Z. And in addition to pose, we have shape parameter, which is a 10-dimensional vector, and we can represent different sort of meshes by changing this 10-dimensional vector. And given this pose and shape, we give it to a simple model and it generates all the vertices that we need for representing this mesh. And this N that you can see here is in fact 6,890 different vertices, and each of them are represented in a 3 dimension, but this is the actual coordinate and says where it is located in a 3 dimensional space. And yeah, I guess that's enough about simple. And knowing this representation, let's just talk about the TokenHMR. But one thing that you should also know that in addition to the pose and shape, we also need something called camera translation, and that says how much we should translate in the camera coordinate to align the predicted 3D human mesh with the image. And just to give you an example, let's just say I have an input image like this. When I say we have an accurate estimation, that means two things. The first thing is that we can correctly regress the 3D pose by outputting the correct pose and shape, but the other thing is about this camera translation that tries to align it with the image evidence. But unfortunately, current models cannot do both. Why? Because of having a noisy camera model. And if you read the HMR2 paper, for example, you see that they are using a fixed camera model. That means all the camera intrinsic parameters like focal lengths, they are fixed. But at inference time, when we capture an image with our camera, each camera has a different camera intrinsic parameter. So once we want to use this noisy camera model and fit this 3D human mesh into an image, we have no choice rather than estimating a wrong pose so as to better align it with this image. And if you don't understand what I'm saying, let's just see this example then. Let's just say we have these two images from a person with a backpack that is walking. When we look at how this image is captured, we see this camera at the eye viewpoint, meaning that the distance between the camera and the upper body of this person is less than the distance between the camera and the lower body of this person. But why this is important? Because it creates an artifact that makes the lower body foreshortened. And when I say foreshortened, I mean that the lower body is appearing to be shorter than what it actually is. And to me, it was a bit ambiguous to understand that. So I googled it and I found this beautiful image that it shows this marker and it tilts it towards the camera. And let's just define some distance, like the distance between the bottom of the marker until some point in the middle. As I tilt the marker towards the camera, we see that the distance becomes less and less and less. And we have kind of the same issue once we capture the image from the eye viewpoint, because the distance of the camera to this point of the marker is less than the distance between the camera and this point of the marker. And that makes the lower portion of the marker to appear to be shorter than it what actually is. And we have the same issue here, that you see that the lower body of the person appears to be less than it what actually is. But why this foreshortening issue matters? Because once I predict the pose and shapes and I want to align it with the image, what I care is the 2D pose, right? So I can just extract the 3D joints from the mesh and align it to the 2D and try to minimize this loss between the predicted joints and the joints that we are having here as the ground truth. But since I'm using a noisy camera model, after the projection, it doesn't have the actual intrinsic camera models, so we have a noisy projection. And since the lower body seems to be shorter than what it actually is, it creates an artifact that once we look at the HMR2 output, it seems to be wrong. Like you see that it bends the leg from the knee so as to align it with the image evidence, but that's not true. So how this TokenHMR tries to solve it, they use a synthetic dataset called Bedlam from CVPR2024. And this synthetic dataset has some video animations with a perfect ground truth. And when I say perfect ground truth, I mean that I have a perfect pose, a perfect shape, and also the perfect camera model. And having this dataset, they have done some analysis with it. The first analysis is that they picked some frames of this dataset and then they use HMR2 to predict some 3D human mesh. And as you can see here, it seems to be aligned with the actual image evidence. And this is the visualization of HMR2 in 3D space. And this is after projecting it in 2D that you see it kind of makes sense. But the thing is that the ground truth doesn't seem like this. And one thing that they tried to do with this is that they said, okay, I have the perfect ground truth, right? What if I use the perfect ground truth and use the noisy camera model from HMR2 to align it with the image? And if you do this, this happens. That you see that there are some differences between the HMR2 prediction and the actual perfect ground truth. But if I use the noisy camera model from HMR2 to align it with the image evidence, it doesn't align. So you can see that here the mesh doesn't align, and if I extract the main joints and project it to 2D, there's something definitely going wrong. And they have done it with a different example and saw the same issue, that here I have the HMR2 prediction, it kind of aligns with the image evidence, and the 2D poses extracted kind of makes sense. But if I use the actual ground truth and align it with the image evidence with the noisy camera model of HMR2, it kinda seems to be wrong. But how wrong is it? Because this is some qualitative analysis, right? If I want to quantitatively see how wrong is this, they looked at the 2D projections, like the ones you see on the last row, and then they measured something called PCK, which stands for percentage of correct key point. And if you don't know what that is already, it just looks at the error and see if it is within some distance, like half of the object size or the total of the object size, then they consider it as true, and other case they consider it to be wrong. So you can see that in HMR2, PCK of 0.5% of the object size is 78%. So 78% of the cases, it estimates to be within some distance that it is half of the object size. But what happens if I use the ground truth and measure this PCK? Well, with ground truth, we expect this PCK to be 100% accurate, right? Because that's the perfect ground truth. It should perfectly align it with this image. But if I use the noisy camera model from HMR2, as you can see here, it doesn't align with the image evidence. So there's something going wrong. But how wrong is it? You see that the PCK now is dropped to be 66%. So even if I have a perfect estimation for pose and shape, I cannot align it with the image once I have a noisy camera model. So my deep learning model has no choice other than making the estimation wrong so as to align it with the image evidence with the noisy camera model that we use. But then now the question that they also asked is that how bad this 3D human estimation can be while maintaining good 2D alignment. And to answer this question, they used a process called Simplify from ECCV2016 that, given an image, it extracts some 2D poses and it then tries to fit a 3D mesh that perfectly aligns with this 2D pose. And for doing it, you're using a loss function, which is this thing, that from the 3D mesh, they extract the 3D joints, and then they translate it into 2D using some camera model, and then they take the difference between the estimated 2D and the actual 2D, and they try to minimize it. But here they want to see how bad the model can be in 3D while having a kind of perfect 2D alignment. So they added one term to the loss function that you can see here, that they look at the 3D joints extracted from the mesh and take the difference between that and the actual 3D joints, because remember on Bedlam dataset I also have the 3D joints, the perfect ones, and I try to maximize it or minimize the negative one. So if I maximize the 3D one while minimize the 2D one, then I expect to have some estimation that's perfectly aligned with the image evidence, but the 3D one should look to be garbage. And it actually happens. Like as you see here, for the first column, I have the ground truth 3D human mesh and also a perfect alignment with the image evidence. But on the second column, as you see, the 2D alignments doesn't change because I try to minimize it. But as you see on the second row, the 3D one becomes garbage. So with a large difference in 3D, I have the same 2D projection. And that means if I have a noisy camera model, if it is too noisy, then we are likely to have a garbage 3D while have a perfect alignment in 2D. So hopefully it makes sense. And now let's just see what they have proposed to solve this issue. They are proposing a new loss function called Threshold Adaptive Loss Scaling, or TALS. And the definition is very simple. They just look at the difference between the estimated post parameters and the ground truth post parameters, and they try to minimize it, but only if the loss function is larger than a threshold. If it is less than a threshold, then they do the same thing but multiply it with a scale. And this scale should be a very small value so as to penalize the model less. But why penalize the model less? Because they say if it is larger than a threshold, then okay, let's just try to minimize it. But if it is less than a threshold, since we are using some noisy camera models, then we are likely to have a perfect 2D alignment while have a garbage 3D. So try to penalize the model less in those cases. And for the data sets that we don't have any 3D ground truth and we have only the 2D joints, they do the kind of the same thing. They look at the estimated 2D joints and the ground truth 2D joints and they try to minimize it only in case that we are larger than a threshold. If we are less than a threshold, multiply it by a small scale. So now the question is that how we can come up with these thresholds. Let's just talk about how we can come up with the 2D threshold first. They again go back and revisit the Bedlam synthetic dataset that they have, and then they look at the perfect 3D ground truth that they already have, and then they extract the 3D joints from this mesh. Once we have the extracted 3D joints, we can project it to 2D, but with not the actual camera model, but with the noisy HMR2 camera model. And now we have some noisy 2D key points. Let's just look at this and the actual 2D key points that if I use the actual camera model I achieve and try to calculate the L1 distance between these two. And do it over all the training data and use the normalized average of these distances as the threshold. So what that means is that if I use a noisy camera model like HMR2 and I have some distances and there are less than this distance, then that means I'm kind of overfitting to that noisy HMR2 camera model. And how about the 3D one? They use another approach. Again, they use the Bedlam dataset. They look at the ground truth, run the HMR2. HMR2 gives us another output that you see there are some differences, like the lower body is different, the location of the hands are kind of different. And then they extract the 3D joints again. And once the 3D joints are extracted, then they take this geodesic distance, that what it tries to do is that it just tries to minimize the distance between them 3D joints, but in a mesh. So in the mesh, it tries to go and find the minimum distance and tries to minimize it. And then they average it over all the training data and this bedlam, and they use it as a threshold. And by the way, if you're interested to see what are these normalized distances, just go and see the supplementary material of the paper, and you can see the numbers. So okay, this is about the loss function they proposed. They also proposed some tokenization process that let's just talk about it. So for the post parameter, they are essentially trying to find some autoencoder architecture that encodes this post parameter and tries to decode it again. And for that, they use vector quantized variational autoencoder. So let's just talk about that. In VQVAE, once we have this post parameter, it goes to an encoder, and the output of the encoder goes and will be compared with the codebook. But before talking about the codebook, let's just see what is the output of this encoder. The output of this encoder is something they call continuous tokens. So it is a set of tokens. Let's just say this M is 160, and that means I have 160 tokens as the output of this encoder. What is the dimension of each token? It is what they denoted in the paper as DC, and this DC is 256. So I have an encoder, it receives these post parameters, it outputs 160 different tokens, and each token is 256 dimensional vector. And then they define a codebook. And the codebook is again a set of vectors, which this K is 2048. So I have 2048 different vectors, and each vector again is DC dimensional. So in the codebook, I have 2000 different tokens, each are 256 dimensional again. And what I do with this codebook, once I have the output of the encoder, I use this formula that, as you can see, it picks each one of the outputs of the encoder, Zi, and then take the distance between Zi and each of the vectors in the codebook. And they try to see which one of the codebooks has the minimum distance. The one that has the minimum distance is picked, and the value is stored in the Zi hat. So essentially, I have 160 different tokens as the output of the encoder. For each of them, I assign it to one of the 2048 vectors I have in the codebook. And once I do this process, I pass these new discrete vectors to the decoder to reconstruct these poses. And if you don't know how this works, then just Google it and find some YouTube videos about this VQVAE. But in a nutshell, they just randomly initialize these 2048 different vectors, and they then try to train it in addition to the weights of the encoder and the decoder. But what's the intuition behind it? They say, okay, this post parameter has the flexibility to be anything. Like the head can be rotated in some ways, like let's just say 180 degrees in some axes that it is not physically plausible. So how can we get rid of it? We define some discrete simple post tokens as some prior and map all the things that we can see in the training data in these discrete simple post tokens. And using this autoencoder structure, we want to limit the flexibility of outputting any sort of post tokens as the output. And once this tokenization is done, they go to the second stage, which is this TokenHMR. And TokenHMR receives an input image. It goes to a backbone, which is a vision transformer, exactly the same one that is used in HMR2 paper. And then the output of this vision transformer goes to a transformer blocks, which in HMR2 outputs the poses, global orientation, which just goes and looks at the position of the sacrum and sees where the 3D human mesh is oriented, and also some shape parameters and camera parameters, which this camera one is just translation and translates it in the image so as to align it with the image evidence. But in TokenHMR, it does everything exactly the same as HMR2, but for poses, it does some other thing. For poses, instead of directly outputting this theta parameter, it does something else. It says, okay, I have some different sort of tokens that you can see that in the paper they denoted as the Q, and this Q says I have 160 different tokens. Each of them now are 2048 dimensional vector. And it goes to a softmax. I will talk about it why. And then it will be multiplied by this codebook, which we have 2048 different vectors. Each of them are 256 dimensional vector. So let's just see what happens. They say, once I want to use this TokenHMR to output poses, a naive approach is just to use this pose classification to directly find one of the pose tokens in 2048 different poses that I have. But the problem with that is that I need some argument which is not differentiable. So instead of that, they thought about something else. They said I can output this Q matrix, which says for each of these 160 vector, I have to find a weighted average of all these discrete simple pose tokens. So I pass it to the softmax so that they sum to 1, because in the weighted average, the weights should be summed to 1, right? And then it will be multiplied by this CB, and it says just do the weighted average of all these 2048 dimensional vector. And they do it for each of these 160 output vectors. And at the end, we have 160 different tokens, and each of them are 256 dimensional again, which is the thing that the decoder expects, so we can pass it to the decoder and achieve this pose parameter. But note that here in the second stage, they keep the codebook and the decoder frozen. Why they do it? Because we have already learned a pose prior, and for that they use a large motion capture dataset like AMAS and MOYO. And for the images that we have less data, we can use this frozen codebook and the decoder as a prior so as to reduce the flexibility of the model to output any sort of poses and just give the poses that are physically plausible, kinda. And that's the whole idea behind TokenHMR, this type of tokenization in addition to the Tails loss function. And now let's just see some results. The first result should show how to alleviate the 3D degradation problem because of the noisy camera model that we have. And they have provided the table that on the first column you see different training datasets. The SD stands for standard datasets, and they use some videos that they are recorded in a laboratory environment with some motion captured ground truths, like human 3.6M dataset, MPI INF 3DHP dataset, and MPII dataset. This BL is the Bedlam dataset that I just talked about. It's just some synthetic dataset that we have a perfect camera model in addition to the perfect mesh. And they have used different methods, and they have tested it on EMDB dataset, which is a video dataset out in the wild that the camera is moving in addition to the person, and also 3DPW dataset. And the metrics that they report is MVE, which stands for mean vertex error. So once we have these 7,000 vertices, we take the difference of the estimated vertices and the actual vertices, and then we take the mean, and that's the mean vertex error. The other one is mean per joint position error, that we extract the main joints like the shoulders and the elbows and the knees and the ankles and so on, and we take the difference between that estimation and the ground truth. And the final one is the same as the mean per joint position error, but after applying this Procrustes alignment, which just aligns the estimation to be perfectly aligned with the ground truth, and then they take the distance, which should be always less than NPJPE alone. And as you can see, well, TokenHMR should behave better, right? Because that's the paper is about. But you see that the difference between the third row and the fifth row, both of them are HMR2. The first one is using some real data sets, which are actually recorded with a camera, and they have some noisy camera model, but the other one is Bedlam with a perfect camera model. And you see that once I use synthetic data, the mean per joint position error and all the other metrics, they become less, which kind of makes sense, right? Because in the standard data sets, I have some noisy camera models, but in Bedlam, I have some perfect camera model. So then what they questioned is that what if I use standard data sets that we have some 3D annotations in addition to some other data sets that they have 2D annotations? Because if I have some 2D annotations, then fine, I can estimate the 3D mesh and then extract the joints and then project it to 2D and then apply some loss function. They have done it, and as you can see, both the HMR2 and TokenHMR will become worse. Why worse? Because these 2D losses are after projection with some noisy camera model, and that noisy camera model should make it worse. But if you look at the HMR2 paper, they have done it the same thing, and they showed that once we are using this in the wild 2D datasets, the 2D alignment error becomes better, so we have a better PCK, but it appears to be worse in 3D human mesh. So what should we do? They said, okay, what if I use the same standard dataset and the 2D ones, but add this synthetic bedlam dataset on top of them? Well, when we do it with HMR2, we see that, okay, by adding this bedlam dataset, comparing to without it, we are having better results. But the result is not as good as training with bedlam alone. And adding this standard datasets and in the wild 2D dataset, they all just make it worse. So what should we do? They said, okay, what if I use TALS, the new loss function that we proposed? Because that should kind of reduce the overfitting to these noisy camera models, right? That's what they promised. They use it, the performance becomes a bit better, but it's still not as good as bedlam alone. Okay, now what? What if I do not use this TALS, but use this tokenization that we just saw? Well, if we do it, then yeah, the result becomes better, because that tokenization kind of forces us to output some post parameters that are physically plausible, and yeah, that should reduce the flexibility, make the convergence easier, blah, blah, blah. And you see that now we are having 95.6 millimeters in mean per completion error. Okay, now what? What if I use this TALS, but instead of this tokenization in a quantized way, use it in a usual variational autoencoder thing? They have done it, and they use vposer, which uses VAE instead of VQ-VAE, and you see that the result is even worse than not applying it. So once I apply it, the result becomes worse. I mean, at least on the most metrics. So they said, okay, now what if I use TokenHMR that use vector quantized variational autoencoder and TALS loss function? And now you can see we can get 91.7 millimeters error in mean per completion error. But again, it is not as good as bedlam alone, because in bedlam alone, I could get 88.1, which that 88.1 should be, of course, because of the tokenization, not the TALS. So question that we can ask now, which is not mentioned in the paper, is that why we should even include this standard dataset with the 3D mesh and noisy camera model and also the 2D ones? Well, I don't really know, to be honest, but I've heard that Michael Black, from one of the talks, he mentioned that once we add this real datasets, the standard datasets, and in the wild 2D datasets, in addition to the bedlam, which is synthetic, then we can increase the variety, because the model can see more type of poses, and at the inference time, it should be more robust to some challenging poses. But while we only use the bedlam dataset, then we can see that it usually has better accuracy, because in most cases, we are having some poses which is happen as usual, not some challenging poses. Like the person can have his leg 100 degrees open. That's not something that usually happens. But anyway, that was what we can understand from it. And the other thing that they also tested is this thing that they said, okay, once we are using this VQ, VAE, what we expect is that we should learn a good prior. And a good prior, that means that once I crop 30% or 50% of this person and see like only half of the person, well, of course the result becomes worse. But since I have learned a good prior, then I should output some physically plausible output, and that should reduce the error. And we can see kind of the same thing, that on 50% cropping, with HMR2, the performance becomes around 38 millimeters worse, while with TokenHMR, it becomes around 34 millimeters worse. And the final thing to mention, remember this artifact of HMR2 with this foreshortened issue, once we use TokenHMR with this TALS loss function, the result becomes much better. And yeah, that's all I wanted you to know about this TokenHMR. If you have enjoyed watching this video, don't forget to like and subscribe. Until the next video, goodbye.